Okay, so this is worksheet number 3, angled forces and friction. This is most similar to what we did previous week. We were looking at forces. I'll be explaining this a little bit more. So if somebody was absent, I don't believe there was a video or anything about this, but we did enough of it where we have an applied force that's either up at an angle or it is down at an angle. And so this is sort of what we're doing here. Now, one thing to mention is that in these angles that I'm giving here, this is the actual angle you're using. You're not trying to figure out what the angle is with respect to the unit circle. The angle we're giving is the magnitude of that. We will decide whether it's up or down by our free body diagram, and that's it from there. So although there is another side, I didn't have enough time to create a problem that actually made sense before the bell. So I put it there just in case I did, but nothing's worse than creating a problem that you solve that at the end of it you're more confused than when you actually started. So it's better there's not even touch it. So this is period 4. Make sure. Okay, so we'll read through here. And what I'm trying to say is that in a lot of these different scenarios, different things are happening. Okay, but you're going to be given things that are familiar to you. For example, what direction the object is moving, what the mass is, possibly the angle, the applied force or the tension force, the acceleration. You could be giving the coefficient of friction. But instead of trying to look at what you have and saying, okay, I know exactly the path I'm going to take, eventually that's what we call like mastery. When I say mastery, I don't mean like you're like been teaching it for 10 years mastery. I mean like, can you go into the problem, figure it out, get the problem right? That's what we consider mastery. Technically what the school considers mastery, I think it's 70% or above, but in physics we say 80% or above. So if you get an 80% on your test, the school's like mastery, which in some cases is pretty good. Okay, look here. Mr. Dahlstrom is pushing his new refrigerator, mass of 280 kilograms, across this kitchen to the right. So we're pushing it this way. That is the mass. With a force of 1,800 newtons, so we can call that, since it's not one of the main ones, we can call that the generic applied force, at an angle of 15 degrees above the horizontal. So 15 degrees is theta. Now, you say, well, above the horizontal, below the horizontal. We are going to decide what this looks like. Above the horizontal means that is the horizontal. Above the horizontal will be this. Below the horizontal will be that. Even if we had this below the horizontal, that theta would still be 15 degrees. It wouldn't be negative 15. It wouldn't be 345. It would be 15. This causes a horizontal acceleration of 0.5. And so here we have to realize, well, there could be an A of x and there could be an A of y. The easiest way to decide is if it is moving from side to side, that is 0. The only time we have an acceleration where we're up and down is like the elevator problem or a crane or something like that. So if we're deciding the A of y is 0, then this is 0.5. Okay. Now, I'm asking you to solve for all of these three. So draw free body diagram, friction force, normal force, coefficient of friction, which is what mu is. Although I'm asking you that, you may or may not actually solve it in that order. Just overall, you need to solve for those three. It's sort of a way of giving you a hint there. So we have that. So we'll draw our free body diagram. So it's a refrigerator, or a box, doesn't matter. You can draw like that. I like to sometimes draw the surface so I know, oh, okay, that kind of grounds me. No pun intended. There you go. And all the forces will come out of here. So there's no air resistance. We're not going to be having any air resistance in these problems. If you want to do air resistance, go ahead, go along and take AP Physics. It's actually quite interesting how they calculate air resistance. So go through the forces. Is there force of gravity? Yep. Down towards the ground. Is there a surface? There is, and it's pushing back perpendicular to that. So if the surface is sideways, normal force is going to be pushing up. Like I said, the length of these arrows, not necessarily the most crucial part, just the direction on there. It doesn't mention friction, but it's asking for you to find the coefficient of friction, so that's basically telling you that there is friction, or at least you need to take it into account. And since we're moving to the right, the friction always opposes the motion of travel, and so that is to the left. And here we come to the applied force. It's no longer perfectly horizontal. It is above the horizontal, which means that's the horizontal. So coming out of there, so it's above there. So draw it with I would say draw it big enough so that you can draw the arrow or the arrows there. So that's the applied force. So I'm going to use my colored pencils. If you don't have colored pencils, that's fine. But if you do, I find that helps people kind of split up the directions. Not even colored pencils, but if you have different highlighter colors or different colored pens, that could be helpful. So I'm going to use blue for the X direction. So in order to get here, I need to split this up into its components or make a triangle out of a right triangle. So we'll have one of this to the right, and that is my applied force in the X direction. And then to go up to here, I have to go up. So there's my component, and that is FA of Y. And this angle that we have here, this is theta. Now we did talk about this. I'm not sure if anybody was absent when we talked about this on Friday. How we know basically which one is which of these components is going to get the cosine or sine. Yes, it's connected. It's not always x is cosine or y is sine. In this case it is, but this angle is connected from our applied force, and it is touching the x-axis there. It's connected to it, so that means that this is going to get a cosine. So if you even just putting a c next to that to remind you that that's going to get the cosine and that's going to get the sine. As opposed to other problems we'll look at later where that is not always the case. It could be reversed. And that's our free body diagram. What are our forces that we are going to add or subtract? The FA of x right, force of friction left, FA of y up, normal force up, and force of gravity. Notice that I ignored F of A because I can't add or subtract F of A. We talked about this last week because it's not in the same dimension of that. It's not either up and down or side to side. Even at this point, most people have no idea how they're going to do it. You always start in the x direction and just write your forces. Let it guide you. Every force to the right. And I know it can be a little confusing here because we write our words, we read from left to right. We have to say we have identified the right side to be the positive, so that's what we have to add. So FA of x, so the applied force in the x direction.
Can we cancel out the regular FA?
Say it again?
Can we just cross out the FA up there?
Yeah, sometimes I do that so I remind myself not to accidentally use it on its own. So FA of x is to the right. Nothing else to the right, so we're going to subtract everything going to the left, and to the left is force of friction. Okay, and that all causes the mass to accelerate in the x direction. So the forces balanced or unbalanced in this case, or whatever, have caused us to accelerate there. Hey, I still like to plug it in. I don't like to plug in all the numbers by itself, so I'll simplify it and recognize that FA of x is using cosine because it's connected to this angle here. So this is F of A cosine theta minus force of friction equals m A of x. Why this is helpful, even just writing out this much work instead of just plugging everything, is that let's say that you get to the end and you're like, oh, I've made a mistake here. But then you look back at your work and you basically did everything in your calculator. Unless you have a calculator like mine where it like records everything you ever do for like a long time. That's pretty difficult. So now we'll plug in what we know. Let's see what we know. F of A. We know the angle. We know the mass, 280 kilograms, and we know the acceleration over here. It's actually a pretty massive elevator or massive refrigerator there. Maybe not. About 600 pounds, maybe. Sometimes I look up the actual amounts of these things. Like I did for the softball question where I looked up the actual exit velocity of a home run in order for it to work. Okay, so the mass is 280 times A of x, which we decided was 0.5 because it's not lifting up or down. One other thing I want to mention here is that this force, I had to make it strong enough so that it would pull it sideways, but I had to be careful because I didn't want this force to be too big. If the applied force, like if you're pulling a wagon behind and you start pulling at an angle and you pull it too hard, what's going to start happening to that wagon or the object? Okay, let's say you're pulling a sled, okay? You're pulling a sled at an angle, but then you suddenly pull it too hard. What could happen to the sled? Instead of sliding along, start doing what? It could lift off, okay? So we have to, that's why I said it's difficult. I can't just throw in any force there because it may cause this thing to start lifting off, and that's not what we're dealing with here. So we have enough to solve for the force of friction, so we'll go ahead and do that. I have already solved this, so I don't need to find my work somewhere. Oh, there it is. 1800 cosine of 15, I'll write it here, is 1738.67 approximately, minus force of friction. And it's always good to just make sure we take our time. So I'll have to add over force of friction here and subtract 140. So if I'm being absolutely step by step here, this is what the equation would be. And then I always like to write my force of friction, or whatever my variable is, on the left side of there. No real reason, just habit. There we go. So in this example here, so when we say this is our actual equation, that's the equation we created. That is just telling me what direction I'm in. So we had enough in the x direction, we solved it. If we didn't have enough in the x direction, we would go to the y like we've done previously. Let's now look at the equation in the y direction. This is obviously ultimately going to help us because the equation for a coefficient of friction is the force of friction divided by the normal force. We have the force of friction. Now we need to go about finding the normal force. Now we have two forces up. We have F of n and Fa of y. It doesn't matter which one we do first. I'll do F of n first here. Okay, F of n, because it's up. Everything else up will be added, so plus Fa of y, so our applied force in the y direction. Nothing else is up. I don't want to confuse myself with this applied force at an angle, so everything else down will be subtracted. And that equals the mass times acceleration in the y direction. And so that is our equation there. We determined here that A of y is 0. It's not lifting up or going down, so that's 0. Fa of y, it is not connected, so that means it's sine. That means it's f of a sine theta. What is Fg? What is the equation for force of gravity? Yes, it's mg. Yeah, it's not g, it's mg. And now we plug everything. We know we know the applied force, we know the angle, we know the mass, we know the acceleration of gravity. So we have enough here to solve. Make sure your calculators are in degrees. Now, however you deal with this, raise your hand if you basically figure out what these two numbers are over here and then move it to the other side. So like you do 465.87 minus 2,746.8 and then move it over. I don't like to do that. You can totally do that. I like to itemize things. I add this over and then I subtract that over. Does anybody do that? Yes, okay. I was just wondering. Either way, so if you're watching how I'm doing it, add that over, subtract that over, and we get 2,280.93 newtons. And now we have the other side. This wasn't memorized how we were going to do this. I did as much as I could in the X direction, and I found some piece of information. I then went into the Y direction, I found some piece of information. And it comes to be, for this problem, it's enough information to solve for mu up here, which we can do. There is no units for mu, because it's newtons divided by newtons. And I got 0.70, the coefficient of friction. Okay. I mentioned in the past that this is basically sort of a trifecta of information. You have the X direction, you have the Y direction, you have the coefficient. Okay. You'll need two of those to find the third. In this one, we had the X and the Y to find the coefficient. And the next one, or other ones we've done already, you'll need the Y direction and the coefficient to find the X, or vice versa. There may be other scenarios there.